Hello, in this video I'm going to call it Principal Components Part 1, Background. And then really we're not going to touch upon any principal components. We're going to look at rotating axes and ellipses. And if you're familiar with those, you can really skip this and go to Part 2. But some of the notation here we're going to carry over into principal components. And when we see special vector products in principal components, and we say, oh, that's a rotation of an axis, this video is going to help explain why that's the case. So it's up to you whether you need this background or not. So in here, we're going to look at rotating axes. So are the original axes, x1 and x2, and we rotate this to x1 prime and x2 prime. So, and then we have a point in R2 space, call it P, which x1, x2. And then I use a script for a point and then a non-script for an axis. So let's look at this rotated axis, x1 prime and x2 prime. And what are the coordinates in this rotated system? Well, whatever that value is, that's the x value, that, you know, the x1 prime value of that point, and the value of x2 prime is that value. Well, how do you find it? Well, if this rotated distance is phi and this distance is d, then you can take the cosine of this angle and then kind of, in that, which is the adjacent over hypotenuse, and then solve it, and you can find out what that x1 value is right here. And the same way with the x2 prime value, you take the sine of phi, which is opposite over hypothesis, kind of solve it, and you get x2 prime, which is the value of this here. But what would it be in the original x1, x2? Well, we need this distance, okay? So if this angle, which is theta plus phi, and then we take the cosine of that, then we get this over d, and you can solve it, and you get this. So the x1 value is this. The x2 value would be the sine of this, because it's this distance, you know, time, oh, you know, sine of this angle is opposite over hypotenuse. You can solve it for x2 and you get this. Okay, so but here's a note though. You have to know these angles. You know, you have to know how far you're rotating the axes. Okay, so how do you go back and forth from x1, x2 and x1 prime, x2 prime coordinates? Well, this is what we do. First of all, you have to know theta. You have to know how far you're rotating it. Okay, and then we're going to use the addition properties for sine and cosine on these, right? And that's what this is. So x1 is d times, and then the cosine property, right? And then if you multiply d in here, look at d times cosine of phi is x1 prime. So this becomes this, and then when you multiply the d into that, it's x2 prime sine of theta. Well, anyway, so then the same way here, the d multiplies in, and then you get x1 prime times sine of theta, x2 prime sine cosine of theta, and that's it. So if you know the coordinates in the rotated axes, you can find the coordinates in the unrotated axis, or the original axes. Okay. Well, now that you know x1, x2, and x1 prime and x2 prime, this is a system of equations. You can kind of back solve for x1 prime and x2 prime, and that's what we do here, right? We get these. Now, this here looks like a vector product, so we can write it like this, right? This vector times that vector, you get this. Same way here. But this is a vector, right? A transposed vector, and this is x, if you want to call that a vector. So it can be rewritten, if we call that E1 and this x, then that can be thought of as this. So this is the rotated vector times x, same way here. Now, in some cases, you think of this as a vector or a matrix product. So you put E1 transpose and E2 transpose here times X. And so you're pre-multiplying by a matrix for this rotation. But the note here is that if you know theta, then you actually know what this vector is right here. And that's what this is. That's this vector, E1, E1 transpose. And this is the second vector here. So once you know theta, then you know this and you know that. And so to get the transpose coordinates, you just take E1 prime times the X vector. And X is, X1, X2, and the same way here. And that's how you get the rotated axes for X2 prime. Okay? So now if you know theta, then you can find the rotated axes, and then that's just how you get the coordinates. But if you're just flat out given E1 and E2, the rotated axes here and here, how do you find these axes? Well, you take E1 times X. So this is a vector, transpose vector, and this is a vector. And then that gets you this axis. And the same way here, that gets you this axis. Okay, so now moving on to ellipses. And I had to look that up. I didn't know if it was ellipsi or ellipses, and it's ellipsis, multiple of ellipse. So here, this is the general formula for an ellipse, and x1 squared over a squared plus x2 squared over b squared equal 1. And this is a general form of an ellipse centered about 0, and this distance is a, which is from this a squared, and this is minus a. We have b and b, all right? So, but what if we have this times or equal to c? And I wish, let's see if I got a pen here. Let's put a squared there. How does that change it? Well, if we divide everything by c squared, we get this, which means we're in the standard form. So this ellipse has a length of a times c, and this is a times c, and this is b times c, this length, and this is b times c. And we'll see things like this when we're developing principal components. Now, one more. Here's an ellipse in a rotated axis. So it's sort of along x1 prime and x2 prime, right? So the formula for this in the rotated axis is x1 prime squared over a squared plus x2 prime squared over b squared equals c squared. So what is this distance? Well, it's the same here. This distance was a times c. And what's this distance? It's going to be a times c, and this is going to be b times c, based upon this. Now, that doesn't tell us, well, that's the exact length. But now, what if we wanted this in terms of x1 and x2? Now, the next page is going to be a little tedious, but I think worth it in the long run. So we take this, and now remember, how do we get x1 prime squared? Well, or just x1 prime. Whatever this vector is, so let's call that E1, and this E2. So, you either have to know the angle, or you have to know these vectors. But if you know the angle, then you can determine that vector. And so we're just going to assume we know the vectors, right? Oh, must be given theta or the vectors, E1 and E2. So either one. So if you know theta, then you can determine E1 and E2. Or if you're just given E1 and E2, then we'll just use those. So then this becomes this, right? X1 prime is the rotated axis, E1 prime X, and that's the rotated axis for, the second axis, E2 prime X. It just is. And then this is two vectors, so we write them in vector, so this is E11, E12, the two components. This is X here, and then we square it. And then this is E2 prime, or transpose, and this is X squared. But now let's multiply this out, and then we're to here. right? So that is multiplied to that plus this times that, and we get this. Now, we can square it, eat everything, square this, and then we collect all the terms, x1 terms squared, x2 squareds, etc., and we get this, right? Now, this is actually a quadratic form. So this can be thought of as a quadratic form, which is this. So this is x1, x2, and this is x1, x2, and this is transpose. And then this coefficient is here. The one in front of x squared is here. Now there's two of these, so one of them goes here and the other one goes here. And I left it blank because it's the same. And that's it. It's quadratic form. But the plus here, isn't that interesting? Let's write this as two matrices. Let's put that as one and this the other. This is one, this the other. This is one, and the same way here. And we get this. So this matrix is now 2. And so we just brought down the x's and the c squareds. And now the interesting part about this, that's a vector multiplication. This one can be thought of as E1 times E1 transpose over A squared, that you get this, in the same way here. So this is it. This is an ellipse in the rotated axis, but in terms of the original axis, x1, x2. So what is so mind-boggling cool, if we know the rotated axes, E1 and E2, we can just put in the distance of the ellipse, you know, the minor and major axes, we just put it in this form and boom, we got an ellipse in the transform. And see, we're going to see things like this when we develop the principal components. And then you'll see this and you go, oh, that's just an ellipse, right? And these are the rotated axes because they're orthogonal to each other. Now, big notes here is this could be done in reverse. We could be given the rotated axes and of course the distances, and then work backwards and come up with that formula in the rotated axes. That would be fine. So given the rotated axes, the distances, probably should put C in there too. We can create an ellipse going backwards. Now these ellipses are centered around 0, 0, the point 0, 0. We can actually center it around any point, mu, you know, which is a vector, instead of the origin. Now the origin's a vector, right? It's the 0, 0 vector. By just subtracting off the point that we want to center around. And then this is an ellipse. It's actually a rotated ellipse in the rotated axes. Oh, my pen just died. Okay. Another big note, this is so easy to generalize. So let's say we have a vector in space, or in space. Then if we know the rotated axes, E1, E2 through En, now they all have to be orthogonal to each other, right? Because the axes x1, x2, x3 are all orthogonal, so we need these to be orthogonal. Then this is an ellipse in space. And actually it's a rotated ellipse. And this darn thing is crazy. You know how in two space, the ellipse, you know, can be this or this. And I don't know how this is going to show up on my page, but you can rotate it like this, but then you can also rotate it like that. And then in space, it's, who knows, that's a crazy rotation. And so this ellipse, you know, remember I said you can work backwards, working backwards from this, then you get this. And that is so, to me, just so mind-boggling cool. So we take the rotated axis, E1, and multiply it times the original vector space, you know, x1, x2 through xn. And this is our new, you know, this is what we would call x1 prime. You know, it's the new x1 prime. And then this would be x2 prime. And then so forth. This would be xn prime. So then it becomes just an ellipse in, you know, in that rotated axis. And we're also going to see things like this and like this when we develop the principal components. And then hopefully you'll easily say, oh, those are ellipses. Well, that's all I have for today. Run a little long. The next video, we're going to jump right in and start deriving principal components and optimal linear combinations and etc. Hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.